Hello, good afternoon to all of you.
Good afternoon, sir.
So today, as you can see, we are going to discuss about the integration in Block 5. So this is the last counseling session of your course code BMTC-131. And today, our main focus point of discussion is about integration. So here we have to cover 3 to 4 units. So in first unit, we have to discuss about the introduction of integration, then method of integration, then some reduction formulas, then finally we are going to discuss about the application of integrations. So let us begin with the definition of integration. That means what is the geometrical meaning of definition of integration, and basically we are starting from the definite integral. And as you know, we have two kind of integration. First one is indefinite integral and second one is definite integration. So this formal definition of integration will be discussed in the form of definite integration. So here let us go to page number 9. Look at the formal definition of integration. So here the definition goes like that. Now let us propose on that particular definition of upper sum and lower sums of a particular function in a certain interval. Now, the definition suggests that suppose n is a natural number greater than equals to n, and there is an interval in which the function is defined. So this is the definition of partition of a set, partition of an interval. So here the interval, the lower limit of the interval is a, and upper limit of the interval is b, and we have to partition this interval with this ordered set. Here, as you can see, the points are x0, x1, x2, up to xn, and xn is the last point that is equals to the end point of the interval that is equals to p. So in this way, we can divide a closed interval AB into several small intervals, and here the points are listed in a certain order. And look at the set, this is an ordered set. It is listed in an order x0, x1, x2 up to xn, and that is a subset of the closed interval AB. And this kind of set is now known as partition of set or partition of the interval AB. So this particular definition will help us to define the definition of upper sums and lower sums of a function in a certain interval. So now let us move to the definition of upper sum and lower sum. They are also known as Darboux sum of an integration in a certain interval. So here in definition 2, as you can see, the function f is defined over an closed interval AB set of real number r, and it is a bounded function. And let us define a partition P on the closed interval AB. And in that partition, the points are x0, x1, x2 up to xn. The partition of this particular interval. Now look at delta I. So delta I is the length of each partition. So that means xi minus 1, and small mi is the infimum of the function in a particular interval xi minus 1 to xi. Similarly, we define capital Mi is the supremum of the function in that particular interval xi minus 2 xi. Now, let us define with the help of these notations. With the help of this notation means delta I, small mi, and capital Mi, we can define the upper sum by the notation of the symbol capital U inside bracket E comma F. So meaning that upper sum of the function with respect to the partition P. So here we define in the form of summation. So here summation is very strong. I to I equal to 1 to n capital M I into delta I. So this is the product of Mi, that means the supreme of the function in that interval of delta I. So that will be now represented as UEF. Similarly, we can also define the definition of lower sum, and also that is known as lower Darboux sum. Now that will be represented by capital L, capital P, comma F inside bracket. So this means that the lower Darboux sum of the function with respect to the partition capital P. And we can also define in the same way in the form of summation, and the summation will be very strong, I equal to 1 to n, small mi, that means infimum value of the function in the interval having length of the interval delta I. So these are the two expression we are using to define upper Darboux and lower Darboux of a function in a certain interval with respect to a partition P, in which we have exactly n number of partitions are there, and we represent these as x0, x1, x2 up to xn. So let us discuss how we can apply this particular Darboux to calculate the Darboux sums of a function with respect to certain interval. So now, have you any question about this upper Darboux lower Darboux or partition of a set? Anyone can reply? Hello, hello, can you hear me? Okay. Let us moving to the example, and in that example we are going to discuss how we can use the upper Darboux and lower Darboux of the function in a certain interval. So here the function is given in terms of a polynomial of degree 3, and that polynomial is defined on the interval 0 to 2, close interval 0 to 2. So your question is that we have to estimate the upper and lower Darboux with respect to the partition. Your partitions are also given. So here 0, 1 by 4, 3 by 4, 5 by 4, and 2. So these are the partition set, or a order set in the form of partition. It is already given. So now we can, in solution, we first represent the value of x0, x1, x2, x3, x4 in the form of partition of the set. Now we can calculate the value of length of each interval, and these are delta 1 equals to del x1 minus x2, similarly delta 2, that is x2 minus x1, and delta 3, that is x3 minus x2, and delta 4, that is x3, and difference between x4 and x3. So in this way, very simply, we can calculate the length of each interval. We have partition the given interval 0 to 2. Now let us calculate the corresponding infimum value and supremum value with respect to the corresponding interval of the function. So here small m1 represent as the infimum of the function fx in the first subinterval 0 to 1 by 4. So here 0 is the lower limit of the interval and 1 by 4 is the upper limit of the interval. So now if we observe the functional value f of 0 equal to 1 is the minimum functional value inside this interval of the function. So that's why small m1 will be the value of 1, because here small m1 is the infimum value of the function inside the interval 0 to 5, 0 to 1 by 4. In the same process, we can calculate the value of capital M1. So capital M1 means supremum of the function in the first subinterval 0 to 1 by 4. So here, if we calculate the value of the function at 1 by 4, and that is the maximum value or the largest value, that is supremum value of the function f in that interval 0 to 1 by 4. So in this way, we can calculate small m1, that is infimum, and capital M1, that is supremum, for each and every sub interval according to the given partition of the interval between 0 to. So in the same way, we have calculated in the second interval, that is 1 by 4 to 3 by 4, and here the infimum value is 41 by 16, and similarly we can calculate the supremum value of the function in the interval 1 by 4 to 3 by 4, and here the supremum value in the second interval is 3 by 3, and it is obtained at 1 by 2. So let us focus on the picture to discuss about the particular calculation of lower sum and upper sum of the function at a certain interval. So let us the given figure. In that figure number 5, we have listed that infimum and supremum values of the function in the interval between 0 to 1, and also we can represent 0 to 2. It will be 0 to 2. Just a printing mistake. So here, let us look at the last interval, and here the last sum interval is A5 to A2, A5 to A4. So here the last sum interval is A4 to A5, and A4 is the point at 5 by 4, and A5 is the point at exactly 2. So this is the last sum interval, that is the main focus point of discussion here, to calculate the value of infimum value and the supremum value of the function. So here, according to the figure, if we clearly focus on the interval 5 by 4 to 2, and in this particular small sub interval, if we observe the functional value p5, p6, and p7, and here p5, p6, and p7. So out of all these three values, p6 is the smallest one or infimum value of the function attains inside the interval between a4 to a5, that is 5 by 4 to 2. So that's why we have to represent like that: small m4, that is infimum of the function in the interval between 5 by 4 to 2, is attained in between the interval 5 by 4 and 2. So that value is 5 by 2. So here we have to represent f of 5 by 2 equals to 1. So this p6 is exactly at y equal to 1. That means here the smallest value or the infimum value of the function within that particular small subinterval is 1. Similarly, to find out the supremum value or the largest value in the interval of 5 by 4 and 2, we have to focus again in that particular graph in this particular section, and here P7 is the largest value that attain the function exactly at the point A5, and A5 is at x equal to 2. So we have here x equal to 2 is the point at which the function attains its supremum value, and supremum value will be 3. We are going to substitute the value of x equal to 2 in the given polynomial to get this value of 3. So this is the simple way to calculate the value of small mi and capital Mi, that is lower sum or lower Darboux-Sham and upper Darboux-Sham. So now let us going to calculate the UPF, that is the lower Darboux-Sham of the function with respect to the partition P, and upper Darboux-Sham of the function with respect to the partition P. So capital UPF. Hello.
Sir, sure,
Yeah.
one question. Sir, in
Okay.
second interval and fourth interval, why we take superior value as f1 by 2 and f2?
So let me to show the figure. So here in the second interval is between A2 to A3. Clear?
In between 1 by 4 to 3 by 4.
In between 1 by 4 to 3 by 2. So
Sir,
here,
here
we have to choose here the lowest value will be infimum value and the highest or largest value will be the supremum value inside that particular interval between
hmm,
A2 to A3, and they will be represented by small m2 and capital M2 as it was
okay, sir.
listed previously here. These are at 1 by 4 and at 1 by, clear,
2. Okay, sir.
at 1 by 2, because clearly 1 by 2 lies inside this interval of 1 by 4 and 3 by 4, and
Yes, sir.
exactly at 1 by 2, exactly at 1 by 2, look at the point P3, that red mark. P3 is the maximum or largest value of the function at this particular second interval.
Okay, sir. Thank you,
Clear?
sir.
Okay. So now
Thank.
we are moving towards the next calculation, and here we are using the direct definition of the upper Darbocham and lower Darbocham. So here in upper Darbocham and lower Darbocham, we are just multiply the corresponding maximum value and its length of the interval, and we are adding each and every value we are occurring from each and every interval. So clearly, as we have here four sub interval, so we have here four terms are there. In addition, so first one is capital M1 delta 1, capital M2 delta 2. In this way, the last one is capital M2 and delta 4. So now we are using all the values occurring in the previous calculation, and finally you can get the value of upper direction, that is UTF 511 divided by 64. So similarly, the same definition has been used here to calculate the value of lower direction, and its value will be 59 by 16. So these are the basic definition of upper Darbocham and lower Darbocham of the function with respect to a partition. So whenever we are going to calculate the upper Darbocham and lower Darbocham of the function with respect to a partition, the value will be different if we are choosing the different partition of an interval. Maybe the interval is fixed, but if we change the partition or partitional point, then obviously the value will be different. So now we are moving towards the definition, that is formal definition of upper and lower integrals, because as we have discussed in differentiation, the value of differentiation or a function is said to be differentiable at a point if lower derivative, that means left hand derivative, and upper or right hand derivative are exist and equal. In that case, we can say that the function is differentiable. So same kind of basic idea has been we have to follow here. And before we are going to discuss about the upper and lower integrals, we have a here small theorem which gives us a relation between the upper and lower Darbochams and the infimum and supremum value of the function. So here the statement of the function goes like that. So we have taken here a function that is defined over an closed interval AB, and the codomain is set of real number R, and that is a bounded function. And suppose you have taken here small m is the infimum of the function throughout the interval AB, and capital M is the supremum of the function throughout the interval AB. And then for any partition P of the closed interval AB, we have this following relation. So here, look at carefully. In the first term, we are using small m as it is the infimum value throughout the interval AB, and it is the product of small m into b minus a. Similarly, second one is lower Darbocham, third one is upper Darbocham, and the last one is again we are using capital M, that means the supremum value of the function throughout the interval AB, and multiplied with the difference or the length of the interval, that is b minus a. So the proof has been given. So the proof has been outlined in the form of upper Darbocham definition. We are using here the upper Darbocham and the lower Darbocham. So in upper Darbocham we have capital Mi and delta I, and delta I can be represented as xi minus 1. Now, as capital M is constant, that can be taken out of the summation, and finally The part of the summation is xi minus xi minus 1. So this xi minus 1 is also called as the telescopic sum because it can be folds up like a telescope. Or finally, you can say that it may be the length of the interval. So that's why it can also be represented by b minus a. So in this way, we can prove the other result of lower Darboxam as well. So here, look at the notations. So particularly we are using this kind of notations to represent the lower Darboxam with respect to a partition in a closed interval AB, and this kind of italic U we are using to represent the upper Darboxam of the function with respect to partition P for the closed interval AB. Now, after discussing this much of upper turbo sum, lower turbo sums, we are now focusing on the definition of upper integral and lower integral of a function defined in an interval of AB. So here we have taken a function f that is defined over a closed interval AB, and it is a bounded function. Then look at the upper integral. So here upper integral will be denoted by, look at this in symbol b bar. So we are using as well, lower limit is small a, upper limit is b, but we are using here an extra symbol that is bar in the upper limit of the function or upper limit of the integration. So this will represent, or according to that one, we can say that that is the representation of upper integral of a function in an interval AB, and that is the infimum of the upper Darboux sum. So here we have to represent infimum of the upper Darboux sum with respect to the partition P of an interval AB. In the same way, we can also calculate the lower integral of the function with respect to the same partition P, and the lower integral can be represented with the help of this bar in the lower side of, or lower part of the lower limit A. So this horizontal bar given in the lower part of the lower limit A indicate that this integration is lower integral of the function in the interval of AB, and its definition is it collects only the supremum value of the lower Darboux sum. So here we have to collect supremum of the lower Darboux sum of the function with respect to partition P in an interval, closed interval AB. So this is the basic definition or formal definition of the upper integral and lower integral of the function with respect to a partition P defined on a closed interval AB. So let us discuss this definition of this calculation with the help of an example. So these examples are given. Look at one of this example. So here in example number 4, it is given like that. Find the upper and lower integrals of the function defined by the function f. The function value will be 0 when x is lies between -1 to 0, and the function value is 1 when it is lies between 0 to 1. So first we partition the given interval into n partition starting from x0 to x, when then we are calculating the infimum value for the function for each and every subinterval, and then the infimum value and supremum value are used to calculate the lower Darboux sum and upper Darboux sum according to the definition discussed earlier in this session, and you can calculate the value of lower integral will be here 1, that is integration from -1 to 1. Look at that horizontal line given in the bottom of -1, that indicates that that is the value of lower integral of the function in the interval between -1 to 1. And similarly, we follow the same process of calculation to calculate the value of the upper Darbocham, and this upper Darbocham will be useful to calculate the value of upper integral. So here this upper integral is also 1. So now we are at a stage to discuss about the definition, that is formal definition of definite integration. So here this formal definition will be discussed with the help of the lower integral and upper integral of a function with respect to a certain partition of a function. So let us see. Again, in the same way, we have to take a function that is defined over an closed interval AB to capital R, that is a bounded function, and we say that f is integrable if the left hand side, that is lower integral, equal to the right hand side, that is upper integral of the function. So if lower integral of the function equals to upper integral of the function are exist and equal, then we can say that the function is integrable in the given interval a v. Now, look at one more this theorem that is well known to us from 10 plus 2 level. So it is integration from b to a f of x dx. If we interchange the limit of the integration, then we have to multiply minus 1. Now another theorem is there, and that is the difference between upper Darbocham and lower Darbocham is less than epsilon. So that will satisfy, because whenever a function is integrable, this condition must be satisfied that the absolute value of upper Darbocham and lower Darbocham must be less than epsilon. So these are the necessary condition for the integrable. So here the integrable is the sufficient condition, the condition for the function to be integrable, but it cannot be a necessary condition here. So some more examples are given. So let us move towards some more points, and these points are is given in the form of fundamental theorem of calculus in page number 21. So let us move to the page number 21 to discuss about the fundamental theorem of calculus. So have you any question till now, whatever we discussed in this session? Anyone can reply? Hello? Am I audible? So here, let us discuss about the fundamental theorem of calculus. So here, the statement of the function goes like that. So the definition of antiderivative. So first to discuss about the definition of antiderivative exists of a function in a certain interval AB. So here the condition is that suppose that we have two functions, small f and capital F2 are real valued functions defined in the same interval of interval AB, and capital F is the antiderivative of small f on the interval AB if these following three conditions are satisfied. So here capital F is differentiable in the interval of interval AB and continuous on the closed interval AB. The function small f is also continuous in the closed interval AB. Then the third condition must be satisfied, that means the first derivative of the capital F must equal to the value of small f for all values of x in the open interval AB. So whenever these conditions are satisfied, you can say that capital F is the primitive of small f. So primitive or antiderivative is the definition of primitive and antiderivative of a function with respect to an interval AB. So now this theorem will help us to find out the antiderivative of a function with respect to a certain interval, and here the antiderivative can be represented like that. So here suppose that capital F and capital G are two antiderivatives of the same function small f on the closed interval AB. Then we can represent capital F dash equal to small f and capital G dash equal to small f on the open interval AB. Then we can also represent capital F of x equal to G plus C. That means there is only a single difference between these two antiderivatives of the same function, and this difference is a constant function C. This difference is a constant function C. So some more results are given. So here, look at the expression in theorem number 8. This particular result is useful when we are going to calculate the integration of a function where the upper and lower limits are in other functions in the form of z1 and z2. So look at this expression. So here we have taken a function small f, and this small f is a function in the form of closed interval AB, which is defined over a set of real number r, and that is a continuous function. And here capital F is the integral value of the function f from small g1 to capital G2. So look at here. Here the lower limit is a function in the form of small g, and upper limit is another function in the form of capital Z G2, small g2. So whenever we have this kind of expression to find out the integration, whenever the limits are also in terms of function of x. So the answer will be like that. That means derivative of an integral. You can also sign the derivative of an integral. So it is dy dx of integration from g1 to g2 f of t dt. So here you can represent, look at that particular integral. So here f, in place of t, we are substituting the upper limit, that is d to x, and then we are multiplying its derivative of upper limit, that is c2, minus again the integrand f, and in place of t we are using the lower limit, that is z1x, and we are multiplying the first derivative of the lower limit, that is z1 dash x. So this is a simple formula we can apply to find out the derivative of an integral. The proof is already given, and the proof we can prove it by using the product rule of differentiation, and that was discussed very simply. So here we are using here theorem number 4. So here the function is represented from a to g2 and g1 to a. That means we are subdivide the interval in terms of a constant term to prove the result of this theorem. So now let us move towards some more basic definitions or basic points of integration in page number 21. That means now after discussing the definition of a in particular function defined on a certain interval, we can now easily calculate the integral value of some basic functions like trigonometric functions, exponential functions, and also some algebraic polynomial function. So let us discuss all these, and that was listed in page number 29. So let us move to page number 29. In page number 29, in the second column, the functions are listed. In the third column, the integration of these functions have been given. So if the function is a monomial with power n, the integration of x to the power n will be x to the power n plus 1 divided by n plus 1. And similarly, if the function will be 1 by x, its integration will be ln mod x plus c. So in this way, all the basic integrals of the function which are basics in our mathematics has been listed in that particular table. So now, have you any question? Hello, am I audible?
No, sir. Yes, sir.
Okay, yes, please.
No doubt, sir. It's
So let us move to the next kind of integration by substitution. So here we are moving directly towards the page number 48 to discuss about the integration with respect to trigonometric substitution. So how we can use the trigonometric substitution to find out the integration in the form of root over in numerator as well as in denominator. So now let us move to the page number 48. So here this table, small table, contains a list of trigonometric substitutions. So here on the left hand side, we may have the functions in numerator or in denominator. So whenever we have this kind of expression or functions, we have to substitute in first case that is x equal to a sine theta, in second case that is a tan theta. Similarly, when there is no root over sine, only s square plus x square, we have to substitute x equal to a tan theta. And calculation procedure will be very similar and basic as we have done in plus 2 level. So these are the examples or proof of this formula have been given in theorem number. So it is advised to please go through these theorems. With the help of these trigonometric substitutions, we can clearly or easily prove all these results. Now we are actually focusing towards the application of integration. So application of integration is in unit number 20, and in unit number 20 we have to cover about the application of integration. And in application of integration we have two small attributes, and these are area under a curve and length of a plane curve. So let us move to that particular definition of area under a plane curve and length of a plane curve. That means how we can utilize this definition of integration to find out the area under a curve and the length of the curve for a particular assigned interval. And these are elaborated in page number 143. So let us move to the page number 143. It's number 96. Application of integration summary under curve. So whenever, so let us discuss this particular figure. So here, if we observe the figure, the graph is drawn for the function f of x, and here the function is given like that. it is a polynomial of degree 3, and it is x minus 2 into x plus 1. That is a polynomial of degree 3, and we are going to draw the graph in a certain interval. So look at the point. So points are represent capital A, capital B. This is the origin O point, C point, D point. So capital B and capital C are the maximum or supremum infimum value of the function in a certain interval. So now our here main focus point of discussion is that area under the curve. So whenever we have a definite integration, or we are going to calculate the value of definite integration, and definitely always definite integration always gives us the area under the certain curve. So look at the expression here. So the point capital A is particularly in the position of -1, and the last point that is intersecting the x-axis, that is capital D point, is exactly at the point 2. That means if we are going to calculate the integration of this function which graph has been drawn, it is listed here. Integration from -1 is the lower limit, 2 is the upper limit. Then the function is written in terms of degree 3 after multiplying all the three factors. Now, very simply, we can utilize the formula of x to the power n to calculate the integration of individual terms of the integrand. And finally, we are using the upper limit and lower limit. And look at finally, we have got a particular value, and this particular value represents the area under the curve. So under the curve means bounded by the curve, we can say that here. So here first section of the area is capital A1, and second section of the area is capital A2. The first section is between the interval -1 to 0, and second section of the interval is between 0 to 2. So this is a simple geometrical procedure or geometrical representation of a definite integration, is that whenever we are going to calculate the definite integration, it always gives us area bounded by the curve and bounded by the coordinate axis. So this is the main focus point of discussion under this particular area of the curve. So now if you have any question, then please. Anyone can reply. Have you any question? Then you may please. So here, look at the calculation. Here we have calculate the definite integration, and we have got the result -9 by 4, and here -9 by 4. And as we discuss here, definite integration always gives us area under the curve, and area cannot be negative. So that's why answer will be always the positive quantity. Answer will be always the positive quantity, that is 9 by 4. And the same can be verified with the help of our definition discussed in the upper Darbocham and lower Darbocham. In the definition of lower integral and upper integral of the function defined over a partition P in a certain interval AB. So the same definitions, idea and formula has been utilized to verify the result we have got in this present example. So here that has been listed in bold letters, that is in general we can say that if the function f of x is less than equal to 0 in a certain interval to interval AB, then we take here that is a negative sign of an integral varies from lower limit a to upper limit b. So the geometrical meaning is to be same, that is area under the curve y equal to f of x from the lower limit a to lower limit b. So such kind of examples are also given in example number 1. And here the example number 1 is described over a circle, and we are going to calculate the area of integration of the function from the interval -1 to 3, and clearly the result will gives us the area under the curve from the interval -1 to 3, and this particular value is the area of the semicircle drawn in the figure number 2. We can also easily verify from the figure in page number 128. So these are the simple basic applications. So this is the simple basic applications of integration to calculate the area under a function with respect to certain interval AB. So now the next application is how to calculate the length of a plane curve, or the length of an interval defined over the x-axis in the domain of the function f. So we are moving towards the calculation procedure or length of the curve using the integral sign, and it was discussed in page number 144. So let us move to page number 144. So length of a plane curve. In length of the plane curve, the same conditions has been used that was discussed in the beginning of this session. That means we have considered here a function f that is defined over a closed interval ab, and the function is continuous, and its first derivative is also continuous. And we have taken a partition in the form of order set x0, x1, x2, xn. So after taking this kind of partition, look at the corresponding figure that was given in figure number 17, that represents the length of the curve, or length of the curve that is represented by the function y equal to f of x. So if we look at the closer value of that particular fixture, look at the circle. Inside that circle, we have a triangle, and inside the triangle, we have an arc from the point xi minus to yi minus 1 to xi to yi. So here, look at the small change in x-axis, that is delta xi, and small change in y-axis, that is delta yi. So these particular values are very much useful to calculate the length of the curve, because if we partition the interval of the function, then the small partitions are represented in the form of x0, x1, x1, x2, like that. And every subinterval we have a definite length of this subinterval, and this length of subinterval are represented by delta xi. So here delta xi is the horizontal component and delta yi is the vertical component of this small section of that particular right angle triangle. So here we can say that the length of this piece of arc, this means this particular arc represent the original curve or original section of that particular function f. So the length of the line between xi minus 1 and yi minus 1 and xi yi will be the approximate value of this particular arc between these 2 points, and that can be represented with the help of this formula that is written here li. That means the length of the curve between the interval xi minus 1 yi minus 1 and xi yi can be calculated root over of delta x square plus square of delta yi, because here delta I is a horizontal component, and delta y is the vertical component of this right angle triangle. So that's why we can use here the Pythagoras formula or Pythagoras law to calculate the value of that particular small length of this line segment. So similarly, after calculating this kind of small piece of length of this particular curve, we can now using the supremum and infimum value of the function to define our desired result in terms of lower integral and upper integral, and finally we have got it the lower integral and upper integral both exist and equal. Then we can say that yes, that is the value of the integration with respect to the interval a to b. So now let us discuss the same idea with respect to an example. So look at that example number 8. In example number 8, the graph of y equal to ln x has been drawn, and we have to propose the interval between x equal to 1 to x equal to 2. X equal to 1 to x equal to 2, it is clearly increasing function. And now from that particular one, here we can use this particular formula as a standard formula. Look at here that was listed in finally this particular formula. So this particular formula is a standard formula that will gives us the length of the curve in the interval between a to b. So here the formula goes like that: integration from the interval a to b under root we write 1 plus the first derivative of the curve with respect to x and the square of that one. So if we are using this small formula, directly we can calculate the value of the length of the curve in the interval between a to b, and the same formula has been utilized here in this definition to calculate the result or length of the curve between the interval 1 to 2. So we have used here capital L, lower limit is 1, upper limit is 2. That means we have to calculate the length of the curve in the interval between 1 to 2. So I can use the formula. We can list it here, root over 1 plus dy by dx whole square dx. So dy by dx means you have to calculate the derivative of y, and as y is given ln x, the derivative of y will be now 1 by x. We are utilizing this value here, and that is the square of dy by dx, that is 1 by x square. So we are using here some algebraic calculation. Now after getting that one, we can calculate this integration value by substituting 1 plus x square equal to t square. And after substituting this relation, we can easily calculate the value of the integration. And after calculating the indefinite integral, we are using the corresponding limit. Lower limit is root over of 2 and upper limit is root over of 5. This lower limit of root over 2 and upper limit of root over of 5 has been calculated from this particular relation, because from this relation we are using here the lower limit of x equal to 1, and when x equal to 1 the value of t will be root over of 2, and when x will be 2 here the value of t will be root over of 5. So in this way you can calculate the lower limit and upper limit of the new integration in the form of new variable t. And by using simple algebraic calculation, we can easily calculate the value of the integration, and this particular value will gives us clearly the length of the curve within the integral or interval between 1 to 2. And in the same process, we can utilize the same procedure to calculate the length of the same curve from the interval between 0 to ln 2, and that has been calculated here in this particular calculation. So these are the two simple applications of integral. The first one is area under the curve. We have discussed how we can calculate the area under the curve of a given function in a certain interval AB. And similarly, the second part of application is how we can calculate the length of the curve with respect to an interval AB. So these are the two main focus point of application in this final unit of this session. So So some other examples are given, and students are advised please go through each and every examples given in your textbook for the better understanding the chapter and the examples. So if you have any question, then please put your question. Hello, anyone can reply. Am I audible? Otherwise, we are going to end the session. And today is the last session of your course BMTC 131, and we have covered integration, definite definition of integration, formal definition of integration, and also discuss the calculation procedure of integration along with the substitution procedure. And finally, we have discussed about the application of integration. Basically, we mainly focus on the two application. First one is area under the curve, and second one is the length of the curve within a given interval AB, closed interval A and B. So have you any question? Priyanka Padi, am I audible?
Hello.
Hello, have you any
No,
question?
sir. No questions.
Okay, thank you. So we are going to end the session. So I would like to thank all of you who are joining in this session of discussion of the last session of this BMTC 131 course code. So thank you once again.
Thank you, sir.